Welcome to Basic Statistical Literacy Part 2. Good morning, and thank you for coming. If you came to the previous session last week, thank you for coming back. If this is your first statistical literacy session with me, though, my name is Morgan. I am a clinical and instruction librarian at the Savitt Medical Library, a part of the University of Nevada, Reno School of Medicine. And today's session, before we get into it, I do want to note that I am operating under the assumption that we're all on the same page as the last session. So I will be referring to terms like population, sample, variable types. So if you weren't able to attend the last session and you don't have working knowledge on those concepts, feel free to, once this one is posted online, maybe revisit it and watch both of those back to back so that everything kind of comes full circle. The session today is a little bit of a reach from being ambitious. These ones are going to be more intensive concepts, but I tried to boil it down as much as I could. Now, before we get started, I did want to do a quick reminder that I named this session Statistical Literacy because the goal here is not necessarily to have you leave the session a practicing statistician. Statistical education is very lengthy for a reason. It takes a lot of time and practice to have kind of a truly applicable theoretical understanding of a lot of these things. And that's why it can be so overwhelming when you see things in academic articles, or if someone is bringing you into a research conversation, things can get really overwhelming really fast because there's a lot of details. So my goal today with statistical literacy is just to provide you a toolkit, a comprehension of the processes and the terminology being used in order to understand the broader information that it's being used in. So that context of an academic article, which we'll go through at the end. And today, the topic is hypothesis testing and distributions, which I think are some of the more, I guess, commonly used statistical analyses, specifically in inferential statistics. So when you're investigating something, you typically use hypothesis testing. But it is also one of the more complicated concepts to go through. So as I go through it, if something is not quite making sense, or if you have any specific questions, feel free to put them in the chat and I can address them as possible at the end of the session. But the most important piece is, before we fully get into it, what even is hypothesis testing? So the quickest and easiest way that I can think to describe it is it's just a mathematical way of answering a question about your data, your population. But in math, we love steps. In science, we love steps. And as you can tell by the use of the word hypothesis, this is kind of a more basic sciences, biological sciences way of approaching math. So rather than asking a question the way that most of us would ask a question, you're doing it kind of the basic sciences way of just making a statement and then you're proving it true or false through whatever mathematical calculations you're doing. And that usually follows a pretty linear step-by-step process, similar to the way that laboratory work can usually be very linear, with, you have to do one thing to be able to do the next. This graphic I enjoyed because it gives kind of a more colorful, engaging representation of that step-by-step process. But this is by no means comprehensive or exhaustive of every step that can go into hypothesis testing. This is just kind of a basic test, what that might look like. So stating what exactly you're going to be testing, then choosing different values from your data for things that you're going to plug into some type of equation. You're going to plug everything in, do that math, and based on that result is whether or not you're proving it true or false. So it's, again, very similar to the basic sciences. It's just math instead. You just have an equation that you're plugging things into. But again, that's not comprehensive or exhaustive. There are a lot of tests that involve highly detailed processes. If any of you have ever been burdened with having to do an ANOVA test by hand, you will understand that hypothesis testing can be extremely involved. But for the most part, you're going to have clear steps. but those steps are only indicated by the type of test that you're doing. So the key takeaway with just kind of the basics of hypothesis testing and what we'll be going over today is with articles and in the terms of literacy, when it comes to describing a hypothesis test, the intent of that test and the steps being taken have to be clearly stated for an understanding. And usually, especially with health sciences, narrative explanations cannot be expected. That's more work than is necessary, so it's not going to be done, which is fine. So typically in articles, you might just see the name of the test completed, and then in parentheses next to it, the test statistic or p-value that resulted, which the next slide is terminology. So I'll explain what those things are. But they like to give you kind of the bare minimum information necessary. So from a literacy perspective, that means it falls on us as the reader to maybe look up in a separate tab the name of the test that's being used so we can see these steps. But sometimes they're nice and they like to give us a step-by-step of what they did. But depends on the person, depends on the time constraint and how much they wanted to go into that. If it's not a statistics-centric article, they probably won't. So that's okay. But that does mean that we have to rely highly on our knowledge of terminology instead, because they're just going to kind of be throwing out words rather than that step-by-step process. And it relies on us as the reader to know what they're talking about. So typically, I kind of listed these in chronological order of how you might use them in a testing process. I did that entirely accidentally. I didn't notice it until this morning. But at the beginning of the process, you do have to state your hypotheses. And usually the terms that you'll hear are your null hypothesis and your alternative hypothesis. Again, not comprehensive or exhaustive. Sometimes you have multiple alternatives. Sometimes there's craziness happening. But for the most part, you'll just have a null and alternative that you're testing. And ignoring what I put in parentheses for a moment, because I know that wording is awkward. I'll explain why it's so awkward. But your null hypothesis is essentially, you haven't proven that anything's different than how you already understood it. So if you're testing for maybe a difference between two variables, your null hypothesis would be there's no difference. We haven't proven that anything exists outside of the baseline we already understood. Whereas your alternative is the complete opposite. Something is happening here that we are asking, is that happening? So with differences, it could be there is a significant difference. There is a difference between these two variables. And our goal is to either prove that that's true or say that that's false, and we're just going to return to baseline. We haven't proven anything. And the reason it's worded as either there is sufficient evidence to prove or there's insufficient evidence to prove is because hypothesis testing is the perfect example that statistics never deals in absolutes. There is no absolutes other than, I guess, absolute values, but that's more of a math joke. But statistics as a whole, you're never saying something is entirely true or entirely false. You're usually just saying we have enough evidence to prove that this is happening, or there's a low probability that this isn't happening. We'll say something kind of conditionary around it. We don't usually deal in absolutes. And hypothesis testing is a really good example of that wording being used heavily. Then you have your test statistic. That's a term that you usually won't hear referred to as that. Usually they will just put whatever letter variable representative they're using for their test statistic. So like Z, T, chi-squared, whatever test they're using. And it's kind of expected that you know that that's what that is. But your test statistic is essentially the results of whatever formula you're using. You're plugging all these numbers that you have into it, and you're getting a value. And depending on how big or small that value is, you're saying we have sufficient evidence, which sounds super arbitrary because just how big a number is determining whether or not you're accepting the alternative sounds a little crazy. which is why people tend to rely more on your alpha and p values being compared rather than just your test statistic and what's referred to as rejection regions. So if your test statistic is bigger than a specific boundary or less than the negative of that boundary, that's when you reject. People like to mostly just use p-values because it's a little more straightforward. It's less arbitrary than just this number is really big. So that being said, in order to understand p-values and kind of the significance behind it, I have to kind of go into what are called type 1 and type 2 errors. So a type 1 error is your risk that you're saying the alternative is true when it's actually not. So you're straying from baseline, even though you probably shouldn't. And type 2 would be the opposite. You're staying in baseline when you have the opportunity to leave. So your alternative is true, but you're keeping your null. And I think the important thing to emphasize here is these aren't errors that are due to your calculation. These aren't errors due to like manufacturer error. This isn't, the math is wrong, nothing like that. These are errors that are completely outside of your control, outside of the researcher's control. So rather than manufacturer error, this is like material error. This is maybe your sample isn't actually reflective of the population and you don't know that. That's always possible. So, the risk of these errors is kind of ever present. You can't fully get rid of it because you can't really control things that happen by chance. But usually with testing, you'll see alpha quite a lot more frequently than beta because especially in something like health sciences research, straying from baseline when you shouldn't is a lot scarier than staying safe and staying at baseline when you can't leave, because especially in clinical research, that's a patient's life. So a lot of health sciences research, you'll see a lot of concern about type 1 error, your alpha values, which is how much possible error you're allotting will be as small as possible. Please, we don't want this error. And the reason why that's significant for p-values is usually you will accept your alternative and reject your null if your p-value is less than alpha, which I know sounds, again, almost just as arbitrary as the test statistic thing, but hear me out. So to define p-value, this is, I think, where I challenged myself a little bit because in statistics forums online, there's a lot of discourse on how to actually define a p-value. I didn't know that it was as controversial as it is. Apparently it is. But how I've always understood it, and I guess what makes sense to my brain, is your p-value that results from, the calculations in your tests is the probability that your results occurred by chance. So it's the probability that something is happening just by happenstance, by an error in your sample, by the wind blowing the wrong way, like it just happened. And so the smaller that is, the less likely something is just kind of happening, and the more likely it's statistically significant. It's something that's happening with evidence that you can prove is occurring. The reason why we reject if your p-value is less than alpha is essentially if we allot, say, the standard that people tend to use is 0.05 for alpha. So you're saying I'm allotting a 5% chance of a type 1 error in this whole thing. So there's a 95% chance that it's not because of an error, which is high, that's good. But if you have a 5% alpha and say you have a p-value of 8%, then there's a 5% chance within that 8% that that is an error. So you only have a 3% chance that that's not happening by chance, if that kind of visual makes sense. So you have a p-value that's greater, then some of that can be taken up by the possibility of error. But if you have the lowest p-value possible, then that can't be attributed to error because maybe you have like a 2% chance it happened by chance and a 5% chance it's error. So you can't attribute that to the error that you've determined. So it feels more trustworthy, I should say. So overall, with all of those complicated definitions happening, the biggest takeaway is with p-values, you want them as small as possible. So if you ever see some type of research poster or any results that just have the p-value and expect you to know what that means, you can assume an alpha of 0.05 and just see how low the p-value is. Low as possible is the best. But with null and alternative, sometimes they won't be stated explicitly. You just kind of have to assume based on whatever their research question is. But if you hear these terms referred to by their actual name, it indicates kind of what step of the process they're talking about, and then also where those conclusions are coming from. So they may say, you know, I got this result from this test, but if they don't give you the p-value or the test statistic, why is that happening, you know? So it's kind of the way that this is happening is indicated by whatever terms they're using. I know that was a lot. I'm sorry. We can all take a breath. There's a lot of terminology with testing, and again, I don't expect you to remember all of this, but the key takeaway is just p-value as small as possible, if at all possible. Now, again, I mentioned that that's not necessarily exhaustive or comprehensive because we have a lot of different types of tests going on. Even this figure that I have on this slide is not at all comprehensive. It kind of just names some main ones that you might see. I appreciated it because it's kind of a decision tree and it follows how I usually like to think about testing. But you have tests that can talk about population characteristics. So you can test for, I think that the mean of the population based on my sample is this value. And I just want to run a test to see if that's true. Or I think that the variance is larger than this or less than this. Another thing you can test for is the distribution of your data, which I will get into. That's a whole can of worms. But that is important information to have, and you can run a test for that. You can also run a test for correlation. So you've probably heard the saying, correlation does not mean causation. Correlation just means that an increase or a decrease in one variable is resulting in an increase or decrease in another one. So any change in one results in a change in the other. But that doesn't always mean that they're actually directly related. The biggest example of that is ice cream sales and drowning deaths are technically correlated, but it's usually just because you're swimming more in the summer and you're eating more ice cream in the summer. That doesn't mean that ice cream is causing drowning deaths. So you can test for correlation, but it's up to you to use your best judgment or the researcher to use their best judgment as to what that relationship actually is. You can also test for the differences between variables. You'll typically see this a lot with randomized controlled trials. So if you're putting an effect on something, if you have a before and an after, or you have a treatment and a placebo, you'll see a lot of these tests for differences because you want to see if anything is significantly happening that's different between two groups. And then I didn't realize this is as controversial as it is as well. I've always seen parts of regression as testing. So regression meaning you can make predictions on future values. You can get a view of what data looks like, both in the sample that you have and also possible expected values. Some people do not consider that testing. That to each their own. Thought I'd throw it on here as a possibility, but apparently that is contested. But all to say, whatever test that you're doing, whatever type of test that you're doing, comes with some baggage. Every test is going to have a different set of assumptions or conditions that have to be met in order for you to perform that test. The biggest and most, I think, make or break one being, what is the distribution of your data? You'll notice that the first step here on the decision tree is, does your data follow a normal distribution? Which sounds wild because what do you mean by normal? But it's an important distinction to make because you can see yes or no lead you to completely different options. So parametric here, if you ever see that word, it's just referring to something normal. Non-parametric is non-normal. But distributions kind of makes or breaks what type of tests you can actually use and have trustworthy results. So when someone names a specific test, they're indicating not only the goal of their question and what they're investigating, but they're also indicating all of these conditions that they have met, so to speak, or you have to assume that they've met these conditions. Unless they specifically state they have, you can't know for sure, but by them running it, it can be assumed that they have met all of them. That being said, distributions are a whole thing, but I'm going to try to give you the most concise explanation that I can. So with distributions, the most basic definition that I could come up with was it is a function, so mathematical function. You have y on one side of the equal sign, x or a different variable on another side. Every change in one indicates a change in the other. That describes possible values and how frequently they can be expected to occur. But it also has kind of a visual representation that I think works better. So this is by no means, I think, the most detailed graphic that it could be, but I thought that it gave a good visual. So with a normal distribution here, the possible values and how frequently they can be expected to occur, you can see that it's very symmetrical. You have your mean in the middle, and things are kind of happening very predictably, kind of equidistant away until you get to the edges. It's normal. That's why they call it that. It's very kind of just expected. This is that bell curve that you've probably heard of or seen at some point in time. It's predictable. And that's why some tests are very specific to normal distributions, because you can anticipate the behavior of this data. So you can kind of just apply any parametric technique and expect it to do the same thing that it would do a different set of normal data. Whereas if you applied techniques that were intended for this very kind of symmetrical, predictable data to something like uniform data or geometric data, you've got entirely different behavior going on here. You've got, everything being equally likely up here. You've got kind of crazy tails over here, not at all symmetrical. So applying methods that are intended for normal data to these other distributions would result in things that aren't really trustworthy, because you're using a distribution that isn't anticipated. That behavior is not predictable to whatever method you're using now. So I don't expect you to necessarily understand or remember all of these non-parametric distributions, but the key is, with specific techniques, normality has to be met for those results to be trustworthy. And on the previous side, you'll notice like any test that just have like a letter, so like t-test or z-test, those anticipate normality. I mentioned ANOVA being really complicated before. That anticipates normality as well. And there are specific tests that you can use with these other distributions, but the big key thing is distribution indicates your expected behavior of your data and what exactly can you use, because some things just aren't going to give you the results that you need. Now, all that being said, I'm going to do kind of a speed run of this article here. Oh, let me go back. Oh, where is it? Okay, I'm going to do kind of a speed run of this article here. Let me copy the link in the chat for you. I'll also share my screen so we can go through it together. But I wanted to show you a representation of data that I think is represented really well, or testing that's represented really well. So this article, I don't claim to be an expert on evolutionary biology by any means. I think it's very interesting though, if you so decide to read it on your own time. It compares the abilities of different species of salamanders to disguise themselves from predators and the different colors and brightnesses that come with that. But they did a really cool thing that I greatly appreciate and is a good example for this, where they not only give you that narrative explanation that I mentioned before, so they're telling you the name of the test. So we have those ANOVAs here, which as I mentioned before, anticipates normality. So we can kind of expect that they are assuming that this data is normally distributed, either because they've tested for it, or it seems to me like their sample sizes are big enough that they can assume that. So that is a concept that is used a lot in testing, is when your sample size is above a certain kind of delineation, usually it's about, like, depending on the textbook, it'll tell you 30 to 50. But usually if you're in the hundreds, depending on the data set, you can assume that the more data you have, eventually it'll spread out to a normal distribution, so you don't have to worry about it. And I'm fairly certain that's the assumption they're making here, because I don't see a normality test named. They also use a 1-sample t-test and a 2-sample t-test down here. So as I mentioned, those whole letters are usually indicative of a normal distribution. And they do what I mentioned before, where they just have kind of their conclusion here. They've found significant differences, and then they just list their test statistic and their p-value, which you can see this p-value is so small, they couldn't even write the whole thing out. There were so many zeros after the decimal. So if that's the case, that's awesome. They've got a lot of statistical significance happening. Rock and roll, good for them. And they do this wonderful thing where I said that you can't necessarily anticipate that someone will give you all of their steps and all of their results. Maybe they'll just give you that p-value, but they give you this whole table here, and they bolded things with statistical significance of the differences. They also, down here with these t-test results, bolded things that had significant results. So they give you their test statistic, which is just t. You don't have to worry about degrees of freedom for understanding it or literacy purposes. That's more for kind of the analysis purposes. I think they just took this window straight out of R, so that kind of default populated. But the key things are usually just the p-value and the test statistic. But as you'll see, I wanted to point out, they bolded these very small p-values. But if you use kind of an arbitrary 0.05, you'll notice there are things on here that could be significant that aren't bolded. So that could indicate either a project-specific goal of having really small p-values, or that could just mean that whatever software they're using only bolds things if they are significantly small. And they don't go off of some type of alpha. Depends on the study. But it is a key thing to note, because maybe in your opinion or your understanding of p-values, you would say, actually, I think the color is also significant, and the brightness, not just the brightness. So I'll take that for what it is. I won't just take the bolded ones. And that is fully up to you. But I hope that with this session, I know I kind of sped through that article there, but it is a fun read. I highly recommend. It's not as fun as the Lego article last week. I don't think anything can beat that one. But I hope that with today's session, reading something with hypothesis testing, you feel a little bit more equipped and a little bit more agency to make those decisions for yourself of what here is significant, what here is not. Yeah, and I think I will call it there, but let me know if there are any questions before we depart. I'm going to switch back over to this screen here. If it wants to switch for me. All right. I think it's on the slides. But yes, that is all I have. If anyone has any questions.